Okay, good morning. My topic for this session will be a very interesting topic, and this will be on long video format discussion on this is AC machines. The subject matter for this morning will be AC machines. This is now lesson number 22. The title of the topic is Maximum Efficiency of Transformers. So for this morning, I will be discussing the concepts of maximum efficiency, and I will try to derive the equation, okay, which will give us the maximum efficiency of the transformer. Okay, let's try to bring out the concept on when a transformer has a maximum efficiency. The efficiency of transformer is maximum when the copper losses are equal to the iron losses or core losses. This will be the condition that will give us maximum efficiency. Okay, let's try to bring out the derivation. This is actually the required formula when the efficiency of a transformer will be maximum. And let's try to derive it, because according to the concept, when the core losses is equal to the copper losses, the efficiency of a transformer is maximum. Okay, let's try to prove this by using differential calculus. Okay, derivation. Efficiency is actually power output over power output plus the total losses. The total losses is the core loss plus the copper loss. Copper loss in terms of current and resistance is actually the secondary current square. If we are to use the secondary value times the equivalent resistance, of course this RE here should be referred to the secondary. This is multiplied by 100%. Okay? If we try to bring out the formula on how to compute true power, we are talking true power over here, right? So true power is actually apparent power times power factor. Because what we call this power factor is actually true power P over apparent power. Apparent power is EI, right? So if we try to compute for the true power, it should be power factor times EI. Okay, I will try to erase this. So the value of the power output is actually apparent power times power factor. This is power. Apparent power is voltage times current, right? So using the secondary values, it should be ES times power factor over ES times power factor plus the total losses. Okay, so this will now be efficiency as a function of all the terms on the right hand side. Okay, let's try to specify what are the constant values on the right. There are 4 constant values on the right, meaning constant parameters. The induced voltage on the secondary is constant. The power factor for any given load is constant. The core loss for any power transformer is constant. And the equivalent resistance is also constant. So what remains to be variable on the right hand side is actually IS. The controlling factor for the efficiency of any transformer is the secondary current. So it seems we are now given efficiency as a function of IS. Okay? So this is now the so-called, under the study of algebra, we are now having a relation of efficiency in terms of the secondary current. Because the for constant ES, power factor, core loss, and RE are all constant. And they are on the right hand side. So we specified the constant values and the only variable is IS. So for the meantime, it seems we are now given efficiency as a function of S. Okay, I will try to erase this one. Okay, let's try to continue. So from the equation, efficiency is equal to ASIS times power factor. ASIS times power factor plus the two losses, core loss and copper loss times 100%. Okay, let's try now to take the derivative of efficiency with respect to IS. Because under the study of algebra, there is a so-called maximum value. Okay? And for what they call this, for a parabola to be opening downward, there should be a maximum value. The graph should be something like this. So this is max value actually. So we are looking for this point here. It seems, right? If we try to relate this to the study of parabola or under the study of differential calculus. So this now falls under the so-called maximization. Okay, let's try to take the derivative. Take the derivative of both sides. The derivative of efficiency with respect to current secondary IS should be equal to. This falls under the derivative with respect to x of a numerator over denominator, right? And under the study of differential calculus, it should be the derivative, sorry for this one. It should be the derivative of the, it should be the denominator, right? Times the derivative of the numerator minus the numerator times the derivative of the denominator all over denominator square. So we'll follow this formula on how to differentiate this one because it seems we are given a numerator and we are given a denominator. So if we try to follow this, okay, the total denominator is actually E is IS times power factor plus PC plus I square RE, it is this, times the derivative of the numerator. The numerator, the product ES times power factor will be constant and the only variable is IS, right? So it seems we are taking the differential of a constant times a function, right? So these two here are constant. What's happening? ES times power factor are constant, right? So the only variable on the numerator is actually IS. So, and we are taking the derivative with respect to IS. And so the derivative of IS with respect to itself, this is 1. Right? Minus the numerator, this is the numerator. AS IS times power factor. Times the derivative of the denominator, this one. The derivative of the denominator, again, ES times power factor will be constant and the derivative of IS will be 1. That's considering this part here. Okay? The derivative of the core loss is what do you call this? Constant, right? So the derivative will be 0. Plus the derivative of IS square RE. But RE is a constant and the derivative of IS square, it falls under the power formula, should be 2 times IS. Okay? Actually multiplied by 1. Because we are taking the derivative with respect to IS. All over the denominator square. The denominator square is here. is power factor PC plus I square RA quantity square. And for maximum efficiency, like what I said, there should be a graph like this, right? And you are looking for the maximum value, right? At that location, the derivative of efficiency with respect to the secondary current will be equal to 0. The slope at the maximum location will be 0. So we will equate this to 0, right? And after equating this to 0, this will be gone, right? So as 0 multiplied by this will now disappear. Right? I will try to erase this one. So no more denominator after equating into 0, because 0 multiplied by the denominator, it will be 0, right? So even this, what you call this, division sign will be gone. Right? So what will come out? I will write this one. E is IS power factor plus PC plus I square RA minus. Okay? There is a common factor. This is, the operation here is multiplication, right? So actually, we can remove this one, ES times power factor. We remove ES, power factor, we remove it. Okay, power factor, we remove it. So what remains? Okay, is IS power factor plus PC, I square RA. What remains here is just IS, right? So it should be IS times this. So IS, first part inside is ES power factor. Next part is 2 IS RA, right? It becomes simpler now. And if we try to expand, this is IS times power factor, PC, I square RA. We try to multiply this, it should be IS power factor. Okay? This is IS and IS will be IS square. This is 2. This is plus and minus. This should be minus. This is multiplied by RA and is equal to 0. And luckily, this part here cancel with this. They are the same, right? So what will remain? It will just be simply PC, right? These two terms here are similar. This is plus 1, this is minus 2, right? So what will remain? This will be gone. Okay, this will be gone. The one that cancels out. And ISRA minus 2 ISRA, this will be gone. It should be negative 1 ISRA, right? Then we place it on the right. On the right. This negative. So if this will be the equality sign, this should be the value on the right. If we transpose it, it will now be plus. This will be gone. So what comes out is the core loss is equal to the square of the secondary current times RA. And it is this formula here. The meaning of this, at maximum efficiency, the value of the core loss should be equal to the copper loss. Because copper loss is actually the square of the secondary current times the equivalent resistance referred to the secondary. Okay? So, according to the concept, the efficiency will occur when the copper losses is equal to the iron losses. And it is proven that after differentiation, what comes out is the core loss is equal to the copper loss. Okay? You got it, guys? Okay? Let's try to compute another or derive another formula. Rearranging this, if we try to compute for IS, it will be the square root of PC over RA. Multiply both sides by ES over 1000. Then the right side, we multiply it by I full load over I full load. So IS, this IS, we multiply it by ES over 1000. We do it also on the right. Okay? And for the right hand side, we multiply it also by I full load over I full load, because I full load over I full load is 1, but we could insert it times the square root of PC over RE. Okay, and if we try to simplify this, IS is actually apparent power. If we try to divide this by 1000, that will now be kVA. Okay, at maximum efficiency equal to IS is still apparent power, but the subscript is different, and this will be actually ES times I full load over 1000 is actually the rated kVA, the rating of the transformer, times the square root of PC over PSC. So at maximum efficiency, the relationship of the maximum kVA and the kVA rated is given by this equation here. It should be kVA rated times the square root of PC over PSC, where PC is the core loss, PSC is actually the short circuit power loss, is actually it's the copper loss, right? Where ES IS over 1000 is the kVA load at maximum efficiency, and ES I load over 1000 is the kVA rating of the transformer. It's the rating of the transformer. And the product I full load square times R is actually full load copper losses. Okay, that's it, guys. That's it. Okay, so we will be needing this formula in the computation of the maximum efficiency and the relationship of the maximum, the total apparent power at maximum efficiency is given by this equation here. It should be the kVA rating of the transformer times the square root of the copper loss over the core loss over the copper loss. Okay? But according to the problem, if PC is equal to PSC, this will become 1, right? This will be 1. And what is the square root of 1? It's either plus or minus 1. Okay? This should be plus or minus 1. Right? We use the plus because there's no such thing as negative thing, right? So a plus 1 or just simply times 1. So meaning to say, at maximum kVA that could be attained by any transformer, it should be equal to the given kVA of the load, okay? If the core loss is equal to the copper loss. But if they are not equal, they are not the same. But according to the concept, if these two here are the same, the maximum kVA is just equal to the given kVA load if the core loss is equal to the copper loss. Okay, that's it, guys. These are the proof that at maximum efficiency, the copper loss should be equal to, or the core loss should be equal to the copper loss. And the proof of this is actually by using the derivative like what I've shown to you guys. Okay, good morning from Los Angeles. This is Professor DavidJDelosReyes. These are the derivation of the formulas for maximum efficiency. The core loss should be equal to the copper loss for maximum efficiency of any transformer. Good morning from Los Angeles.